Assalamualaikum and good day. Today we're going to have a look at two completely miscible solid eutectic system. Eutectic system, two completely miscible solid. A eutectic or eutectic mixture is a mixture of two or more phases at a composition that has the lowest melting point, or a liquid mixture that freezes at minimum temperature. Basically, they are a mixture of components that has lower melting point than their individual compound. It is where the phases simultaneously crystallize from molten solution. The proper ratio of phases to obtain a eutectic is identified by the eutectic point on a binary phase diagram. So the term comes from the Greek eutectos, meaning easily melted. So let's say you have compound A with melting point 100 degrees Celsius. You mix with compound B, which has the melting point 80 degrees Celsius. So these two components mix, we produce mixture of AB. So for both A and B melt together, it must be at the eutectic point. And then there will have melting point lower than the individual compound A and B. Eutectic system. Eutectic point is the point on a phase diagram where the maximum number of allowable phases are in equilibrium. So when this point is reached, the temperature must remain constant until one of the phases disappears. A eutectic is an invariant point. A liquid with the eutectic composition freezes at a single temperature without previously depositing solid A or B. A solid with the eutectic composition melts without change of composition at the lowest temperature of any mixture. So one technologically important eutectic is solder, which has mass composition about 67% thin and 33% lead and melt at 183 degrees Celsius. This is the eutectic phase diagram, which describes the behavior of the alloy, two components of which are completely soluble in liquid state and entirely insoluble in solid state. This diagram has two liquid curves, starting from the freezing point of the two metals and intersecting in a minimum point, E, eutectic point. So on this axis, we have a temperature. This is the melting point or freezing point for component A, and this one is the melting point or freezing point for component B. E is the eutectic point. TE is the eutectic temperature. And on this axis, we have the composition of A or B. So this one will be 100% of A. This one will be 0% of A. And this one will have 100% of B. This one will be 0% of B. On this region, we have liquid A plus B. On this region, we have solid A plus liquid. On this region, we have solid B plus liquid. And then below the eutectic point, we have the solid A and B. Example, zinc cadmium system. When pure liquid of zinc is cooled, it freezes at 490 degrees Celsius at point A. An amount of cadmium is added to zinc and heated to turn to liquid. When it is cooled, it becomes solid and freezes at lower temperature than pure zinc. So adding more cadmium causes freezing point to drop further until finally at 270 degrees Celsius. Meanwhile, for pure cadmium, it freezes at 321 degrees Celsius at point B. So when zinc is added to cadmium, freezing point will decrease. By adding more zinc, the freezing point becomes lower and finally reach at 270 degrees Celsius. So at E point is the eutectic point, which have the eutectic temperature which is 270 degrees Celsius. So at this eutectic point, the eutectic mixture have the composition of 70% of zinc and 83% of cadmium. In this region, we have liquid zinc plus liquid cadmium. In this region, we have liquid phase plus zinc solid. And then in this region, we have liquid phase plus cadmium solid. Below the eutectic point, we have zinc solid plus cadmium solid. Exercise 1. The melting point of X is 232 degrees Celsius and Y is 327 degrees Celsius. The eutectic temperature is 183 degrees Celsius and the composition of eutectic mixture is 63% X. The first question is define eutectic mixture. Eutectic mixture is a liquid mixture that solidifies or freezes at a minimum temperature. Second question, sketch a eutectic diagram for the mixture of X and Y. Label of phases in the diagram. Given information is the melting point of X is 232 degrees Celsius. Melting point for Y is 327 degrees Celsius. And the eutectic temperature is 183 degrees Celsius and the composition of eutectic mixture is 63% X. So sketch a eutectic diagram for the mixture of F and Y. So we have here temperature. This one also temperature. And below here is the composition. So for solid X, it has a melting point 232 degrees Celsius. And then boiling melting point for Y is 327 degrees Celsius. And then eutectic temperature is 183 degrees Celsius. And then the composition for eutectic mixture is 63 of X. So this one is for X. So this one will be 100% X, 0% X. And this one 0% Y, so 100% Y. So the eutectic mixture is 63% of X. Let's say here. Okay, so you draw line here, and then you draw another straight line, and then this one another straight line. At point here is the eutectic point. And in this region is a liquid. This one is solid X plus liquid. This region solid Y plus liquid. And below the eutectic point we have solid X plus solid Y. So at utility point here, we have 63% of X and 37% of Y. So make sure you label all the axis, temperature for axis Y and the percentage of composition on axis X. Next question will be a mixture containing 35% X is cooled from 350 degrees Celsius to the room temperature. Predict the component that will be crystallized from the mixture before reaching the eutectic point. So at 35% of X, so this one is 100% of X, 0% of X. So 35% of X, let's say here. So predict the component that will be crystallized from the mixture before reaching the eutectic point. So you draw a line here. So you will get solid Y. So solid Y will crystallize first before reaching the eutectic point. Cooling curve. A cooling curve is a line graph that represents the change of phase of matter, typically from a gas to a solid or a liquid to a solid. The independent variable x-axis is time and the dependent variable y-axis is temperature. Cooling curve of eutectic mixture of A and B. Cooling process begins when the liquid mixture is cooled from A to B. As the sample cools from A, the temperature will decrease. Along AB is change in slope during cooling. At B, the rate cooling becomes slower. So what happened at point B? Some solid compound B will begin to form. This will lead to a slowing of the cooling due to the exothermic nature of solid formation, but also the composition of the liquid will change, becoming richer in compound A as B is removed from the liquid phase in the form of a solid. B to C, mixture is cooled further until all liquid freeze at the eutectic point at C. C is the minimum temperature which all liquid crystalline or freeze to form a eutectic mixture, and the composition of the liquid phase will remain constant and the temperature will stop changing. Once all of the material has solidified at the time indicated at D, the cooling of eutectic solid will continue at a rate determined by the heat capacity of the two solids A and B and the composition. This is the cooling curve of bismuth cadmium mixture at various composition of 0%, 20%, 40%, 80%, and 100%. Curve L and S, the slope change at point P and Q respectively due to the precipitate formed during cooling process. Heat released from the substance, the cooling process slow down and the slope decline. First section of curve. Liquid is cooled and reach supercooled stage before freezing takes place. Plateau region. Freezing occurs where the temperature remains constant until all liquid turn into solid. At this point, the temperature is freezing point for liquid and melting point for solid. The last section of curve, solid is cooled to room temperature.